Welcome back. In this lecture, I am going to cover molecular theory of corresponding states. Okay, the theory of the corresponding states goes back to van der Waals. So let us first consider van der Waals equation of state. Now, a typical or two parameter van der Waals equation of state is given by this expression, right? Or you can write this in this expression. Now, the A's and B's are calculated based on the fact that at critical point the first and second derivative of pressure with respect to the volume is basically 0, okay, and thus you can obtain A's and B's in this term, which I have written here, that A is equal to 3 Vc Pc, okay, this is the term where B is Vc by 3, which is this, and RTC is nothing but this. Now, if you substitute this in this equation, you get the following, okay, P by Pc plus 3 divided by V by Vc to the power square, V by Vc minus 1 by 3 is equal to 8 by 3 T by Tc. Now, what we are going to define that T by Tc is Tr, P by Pc is Pr, and V by Vc as Vr. So, what we got in expression is basically van der Waals equation of state in reduced temperature, pressure and molar volume, okay. So, that is an expression of that. Now, this equation basically is in this form, okay, and that is what we are talking about in terms of corresponding state theory. So, this implies that this equation implies that if PVT data for different fluids are plotted as PR, VR, TR data, the results for different fluid would be same, and that is basically the hypothesis of classical corresponding state theory, okay. Now, this is quite useful for if you are using molecular models such as Lennard-Jones, where sigmas and epsilons are parameterized, that means they are different for different fluids, but you can get rid of this epsilon and sigma such that everything is a reduced form. Then from the same plot you can extract many different properties, okay, for different fluids. So, that is basically the idea of which we try to make use of it. Let me elaborate on it. The macroscopic basis for CSTs come from the pair interaction and virial coefficient. Let me just go into detail a bit. So, this is the potential model of Lennard-Jones, as we have already discussed that this is a non-dimensional term. So, if you reduce R as R by sigma, okay, then we can get this in terms of reduced potential, where gamma star is going to be gamma by epsilon, this is 4, and you have this 1 by R star 12 minus 1 by R star 6, okay. So, this is something which we have already looked at into earlier. Okay, remember that R's in terms of your T star for the Lennard-Jones is Kt by epsilon, R we know already, and this is something which you can write as a Mayer bond or function, okay. So, where T star here is now simply Kt by epsilon. You can write this expression B2 in this term, okay, which tells you that now B2, if you consider this part, then this is basically dimensionalized. So, if this is B2 is in the terms of the volume. So, B2 if you divide by sigma cube, you are going to get the B2 star, okay, that is what, because this is non-dimensional, okay, this part is going to be non-dimensional. So, whatever is there can be written in this form, where B2 star is non-dimensional. Now, if you extend this exercise for B3, B4 and so forth, then one can show that Bn plus 1, okay, is equal to sigma to the power 3n multiplied by the reduced real coefficient, okay, of higher order or n plus 1th order. And now this understanding I can plug in this virial equational state, which is written here. I can write this Bn plus 1 in terms of Bn star T star sigma q by V to the power n, and thus I got a right hand side which is absolutely independent of the type of molecules, because it is, or it's basically dimensionless. So which means basically if I use different sigma and epsilon for two Lennard-Jones potential, the right hand side is going to be same. Now let me just elaborate also on that. So let us consider two LJ fluids which is given here, which has different epsilon and sigmas. Okay. Now for both of them, for given T star, which is a reduced property, and V star, for both of them if they are same, then PV by RT must be same. Okay. So that means when T star and V star are same, okay, then that is V star, that is T star, if they are same for both the fluids, then that means the right hand side is going to be same. Okay. In that case, the left hand side, which is PV by RT, must be same. Now at a respective critical points here, which means that since V's are same, so we can consider at a respective critical point V1C or V1C star is equal to V2 star, and similarly the reduced temperature, okay, will be same. For simple reason is basically this is at the respective critical point, this expression should hold as well when you have this condition. Okay. So this expression below critical, at critical will be same once you fix this V star and T star. So this, once you fixed it, this expression will be same. Now so you have two equations, one when you have T star less than Tc, okay, Tc here, okay, and when we are considering T star is equal to Tc. Okay. So using these two expression, I can divide it here. When we divide this expression, this is the two equations. Okay, what I get, okay, that P1 V1 T1 P2 P1C V1C T1C, and this will be the for the right hand side, P2 V2 T2 P2C V2C T2C, and this will be when we are considering the ratio corresponding to V1 by Vc, V2 by Vc, and T1 by Tc, T2 by T2. Okay, this you can show that this is the case when this will happen. Okay, and this will indicate that P1 by P1C and P2 by P2C should be same, which essentially means nothing but PR1 is nothing but PR2. Okay, when VR1 is equal to VR2 and TR1 is equal to TR2. So when the reduced temperatures are fixed, reduced volumes are fixed or same for two different molecules or fluids, then the reduced pressure should be also same. This basically tells you or implies that this function is a universal function for Lennard-Jones fluids. Okay. Now this is beautiful because you can, using this expression, you can evaluate many things. Okay. So this is our microscopic theory of corresponding state. Now this particular expression we could evaluate because your Lennard-Jones is basically can be written in this very simple form, which is this here. Okay. So for the case of this, we can come up with the classical CST, and you have this for Sutherland, Lennard-Jones, with fixed N and M. But if this is not the case, such as for the example Square-Well, exponential Kihara, Stockmeyer, okay, with variable NP, then such an expression are not possible to evaluate. Okay. So, the other thing is that for the case of the corresponding state principle, the pairwise interactions are important. This is something from classical statistical mechanics can be applied for. Advantage of this molecular corresponding state theory is that this is applicable for both equilibrium and transport properties, and it can be extended to mixtures. Now, given this information, we can evaluate or estimate epsilon and sigma, because for Lennard-Jones reduced critical point is known and reduced volume is known. So, the reduced critical point is 1.32, reduced volume is 0.77. Now, given this information, you can easily evaluate the epsilon, okay, and sigma for Lennard-Jones model, because you would know Tc of, let us say, methane, and you would know Vc also correspondingly Vc. So, from Vc knowing that this is 0.77, you can obtain sigma. Similarly, 1.32 multiplied by Kt known from the experiment, you can evaluate epsilon corresponding to Lennard-Jones model for that particular fluid. Okay. So, let me try to extend this corresponding state to more complicated molecules. Various approaches are possible. Usually a 3-parameter CST is considered. Most widely acceptable third parameter is the eccentric factor, which basically takes care of the shape. Based on the experimental observation, a simple fluid is considered when you have Psat by Pc, that means Psat reduced Psat is equal to 1 by 10 at T by Tc is 0.7, and we consider fluid to be complex when reduced Psat is less than 0.1 at reduced temperature of 0.7. Okay. So, using this information, we defined eccentric factor as simply the deviation from 0.1 in a logarithmic scale. So, this is Psat at T is equal to 0.7 Tc divided by Pc, okay, log of that minus 1.0. Okay, so this is our eccentric factor. So, for the simple case, simple fluid, the eccentric factor should be 0, because this is going to be 1 by 10, and which will cancel out this, and W should be 0. For complex, W will be greater than 0. The 3-parameter CST states that all fluids with the same eccentric factor are characterized by the same equation of state in reduced unit. In other words, we have the same corresponding state principle, but now you have 3 parameter. Using this 3 parameter CST, the property can be characterized by this equation of state, okay, in a reduced form. So, the W here in subscript indicates that this is basically equation incorporates the eccentric factor. So, very good approximation, except for highly polar or hydrogen bonding fluids. The problem is that we must find out f of W for each value of W. Now, various authors try to establish this macroscopic basis for eccentric factor, and typically people like Lee Kessler and others have extensively worked in this area. So, here the usual way to add this contribution is by considering the case of simple fluid here, plus add the term which is due to the eccentric one. That is why you have Z0 PR TR and W Z1 PR TR. Okay. So, let us try to understand this, how to deal with this. Okay. So, I will come back to this part. Let me just first describe this Virchow equation of state for the mixtures. For the mixtures, we will consider the same expression, but now the V2s, B2s, B3s and so forth will be a combined value for the mixtures, which typically written here as B2 is summation, double summation of Y1 Yj, the composition multiplied by B2 of Ij, where B2 Yj can be related to the Mayer function as we have already seen, except that Bij contains e to power minus beta Ij minus 1. So, this becomes that interaction parameter or potential energy between the unlike species I and J. Similarly, B3 is a triple summation where we consider yi, yj, yk, b3, ijk, where y range from 1 to m and so forth others. And B3 is more complicated expression where we consider 3 mere bonds. Okay, so I won't go through in the details of that. Okay. Okay, so we can consider volume explicit term, or as well as for mixtures you can also consider pressure explicit terms. Okay. Now let's go back to the corresponding state here. From microscopic corresponding state theory, we always try to use this potential model having this kind of expressions where you have epsilon is outside and f is just a function of reduced distance. Okay. Now for B2 we have already evaluated that B2 can be reduced by sigma cube, getting B2 star as a function of T star, or we can consider B2 by Vc is equal to G T R, where G is some universal function for all fluids with interaction parameter. Now empirically people have tried to use or obtained this term in terms of TR. So one of those is Maclaurin and Porter. They have tried to come up with this expression. This is for small non-polar molecules and lower alkanes. Now this has been extended for mixtures also. So for mixtures we have already discussed this. Okay. Now given that potential model is this for which this is applicable, the average distance of sigma ij is considered as the arithmetic mean of the individual sigmas. Epsilon ij is considered as a geometric mean, that is due to the Bernoulli mixing rule. Now this implies that I can consider Vc ij as simple this, because sigma can be considered from here to the power 3, and Tcij is nothing but Tc, geometric mean of Tc1 and Tc2, or Tci and Tcj. Now having this information known, the virial coefficient here can be only modified for Vc ij and Tr. This is Tr, this was Tr. Now Tr can be given as here Tc T by Tc ij. Okay. So the same expression as was found by Glaschen and Porter can be utilized to obtain V2 from B2 from the experimental data. Okay, or in general these correlations can be used. So for non-spherical molecules, the microscopic CST can be derived for Stockmeyer 3-particle non-spherical fluid. Now typically for non-spherical fluid we have come up with an expression which is given here. The B second virial coefficient contains RTC by PC. This is a term which is due to spherical, and this is the contribution due to non-spherical nature of the particle. This is a commonly used expression. For non-polar gases, many different expressions have come. The Pieser-Curl expression suggests this term where B0 is this and B1 is given by this, which depends on Tr. Remember that B is only dependent on temperature, and that is why only temperature is given here. Abbott has also come up with the expression 1975. This is the expression for that. So plus gives you expression for this. Okay. For strongly polar mixtures, one can use the expression given by Hayden and O'Connell. But of course we don't have to remember this. Remember this is an expression which came up with the extensive exercises. What is important is the methodology to solve problems using these kind of expressions. Okay, so let me just further elaborate on this, that this TCs we have to calculate for determining Bij. We need to find out Tr. Tr means you need to know T versus T divided by Tci, which was shown here, right? So we need to find Tcij. In any case, Tcij is nothing but geometric mean of Tc's, and using the compressibility factor we can get Pcij, and omega ij is given as a simple the average of individual eccentric factors. Now often experimental data on Vc are not available. In that case we use simple this expression where Zc are Tc divided by Pc, and this is the expression which is known. So if you use from this to this, we can show that the Z, the compensating factor, is nothing but the mean value of ZCi and ZCj. Okay. Now this may appear to be a little vague and cumbersome, but the idea here is basically there are many correlations which people have come up with to add on to the critical add on to the second variable coefficients based on the spherical nature, and some of those which we can come up with use that to evaluate the fugacity coefficient, and that is what the whole idea being. Why do we use equation of state is because we want to find out fugacity coefficient in order to determine the vapor liquid equilibrium, or in general the conditions of equilibrium. So let us try to make use of an example here. Now virial equation truncated at second virial coefficient is applicable to vapor phase only for molar volume greater than 2 Vc, where Vc is a molar volume at critical point. It tells you simply that too dense fluid is difficult to represent by virial equation of state, particularly second virial equation of state. Now typically one wishes to calculate the fugacity coefficient for a mixture using the virial equation of state at a given composition, pressure and temperature. So in that case, the typical steps which we like to follow is find Tc, Pc, omega for pure fluids. This we can get it from Pauling et al. And many other literature. Calculate mixing or mixture parameters, calculate Bi's and B, determine molar volume as a solution of quadratic equation, and calculate phi's. Okay. So let me try to explain using an example from the textbook of chapter 5. So for a given mixture butane and nitrogen, the mole compositions are given 0.8 and 0.2 at 461 Kelvin. Both are non-polar, and for non-polar physical expressions are commonly used. So we have to find out basically phi, the fugacity coefficient. Okay. Now what are the things which we can extract from the literature? We can find out the TCs, PCs and other parameters. So let me just summarize it here. For butane, which is molecule 1, we have TC given here, PC molar volume, eccentric factor and compensatory factor at critical point, or ZC, is given to us. Similarly nitrogen is given. So now what we want to find out is basically the second virial coefficient for the mixtures, which from the expression should be this y1 square b11, that 2 y1 y2 b12 plus y2 square b22. Okay. How do we calculate B's? We also know that B is RTC by PC, and this is which has a component of eccentric factor, and this is not 0, which means they are not simple fluids. Nitrogen is, but not the one which is butane, and if you mix it, of course it is not, and then thus this will contribute something. Now let me find out first the TR. Now the T is given to us 461. Using this we calculate TR1, TR2. Okay, so from here we can find B11 and B22 using the expression of B0 and B1 using Pearl expression. So let me write down here, or let me go back and look at this expression again. So this was a B0 which depended on TR, and this is a B1 which depends on TR. Now for individual butane and nitrogen we have calculated TR, so we will be able to calculate B0 and B1. Once we calculate B0, we know TC and PC, we calculate B's here. That means B11 and B22 we can now evaluate, and that is what we did here. We evaluated B11 and B22, which came out to be this. But what about B12? So in order to calculate B12, we need to find TR and omega. So to calculate TR, we need to find TC12, and we can use geometric mean of TC1 and TC2, which is what we have calculated here. So we got an expression of 11, but what about omega? So omega again we have discussed earlier, that we will just take out the average value of it. So this is the omega here. Now given this, we can directly make use of B12. So B12 is again we can use it here. Okay, we can use it here, and the TC is there. Okay, we calculate TC, we can calculate B0 because we have the information of TR. We can calculate B1, we have the information of TR. We know W12 also, but what about PC? Okay, so we need to find PC12 also. So we know that ZCIJ is basically, we can take the average value of it. Now ZC, if you take the average, we know from here we can get in, we can make use of the average value of this, and also the mean value of sigmas, and using that information to obtain VC12 also. So using this, we calculate this. From there we calculate the PCs. PC, once we know, we have now B12. PC of 12, once we know, we have B12, which is calculated. Now you plug in these expressions of B11, B12 and B22 in a B mix expression which was here. Okay, so we obtained the value which is minus 178.3 cc, which turns out to be within 4% of experimental values. So pretty good, in that way. Very nice exercise. That means B's are good enough for such a system to evaluate. Now the reason for these good results is because the components were well behaved. It was non-polar, no hydrogen bond, and that's why it worked well. Using this expression, now you can obtain phi. So you have the information of B mix, considering the virial equation of state truncated till second virial coefficient. You can write this expression to obtain V, the molar volume, and this will be in this way. So now once we know the molar volume, you can use this expression of fugacity, okay, and you can show that this is nothing but this. You can go back to the basics of the ln phi and show that this is nothing but this. Now instead of this explicit volume, you could have considered the pressure also, and in that case for low pressure we can use such an expression. We could get this expression based on the second virial coefficient equation of state for mixtures. Okay, so I won't go to the details how it is. It's a straightforward exercise from the basic definition of phi with respect to the integral of terms where the integrand contains the molar volume. Okay, so you can extend the exercises by considering the third virial coefficient for the mixtures. So I'll just write down here. So this will be the case where if we can evaluate for the third, of course it will become much useful and more accurate. The only problem is that it is more cumbersome. Okay. So this is a typical C mix. We can write in a more compact way, as we have shown earlier. Cijk. Okay, where Cijk is nothing but, of course, the second virial, where Cijk is nothing but the third virial coefficient. Okay. Now experimentally, you can write this virial equation of state. If you recall that the way we calculated virial equation of second virial coefficient is by considering density very approaches towards 0, and that's why we took the first derivative of the expressions with respect to the density and obtained the intercept to obtain the second virial coefficient. Now in order to obtain this cross coefficient, we need to find out significant amount of experimental data, and I won't go into details of this, but let me first write down the Z mix here, which is PV by RT for the case of the mixtures. So earlier we said that we just would be considered second virial coefficient truncated version, but if you want to add this and somehow you can obtain this, then it would be very useful. Okay, so you can use this expression and obtain your fugacity coefficient, okay, and if you can do this exercise for this term, you can show that ln phi I is 2 by V summation yi bij plus 3 2V cube summation double summation yj yk cij k minus ln z mixed t. Okay. Now this is quite cumbersome in some sense, okay, where of course our difficulty will lie in getting this mixed cross third variable coefficients, and for that we need significant experimental data, and typically these are very difficult to evaluate. But you can show that using the similar approach as we have done for second variable coefficient, you can also try to do the same thing for third variable coefficient to evaluate these coefficients. Now I hope that this discussion helped you to understand the corresponding state principles, applications of variable coefficient states, okay, and particularly second variable coefficient based using different correlations, and introduction of eccentric factor to incorporate non-simplicity of the fluids such as the non-spherical particle, and using that how to obtain fugacity coefficient. And this is important because this is something which we use in order to incorporate the fugacity information for the gas phase to evaluate the phase equilibrium conditions. Okay. Now with this, I think I will, with this I will stop, and we'll come back in the next lecture with a new topic. We'll start the activity models, or particularly the liquid phase mixtures. So I'll see you in the next lecture.